Hello students, welcome to Kcet JE Neet classes on the chapter Structure of Atom. In the previous two videos, we learned level 1 and level 2 questions. The questions which are asked in previous years that we are concentrating. In today's session, that is level 3, we are going to concentrate more on previously asked Neet and JE questions. If you have not yet watched the previous two videos, I will give the link in the description box and I request you please go through those videos first and you can watch this video. Let us begin today's session with the first question. Question number 1. There are 4 orbitals given. 4d, 5d, 5f and 6p orbitals are arranged in the order of decreasing energy. The correct option is, there are 4 options given. Dear students, to find out the energy of orbitals, we have the n plus L rule. N plus L rule, where n is principal quantum number and L is azimuthal quantum number. Let us go with first option. We have phi of orbital. Apply n plus L rule. N is 5 plus L value for S is 0, for P is 1, for D is 2 and for F is 3. So 5 plus 3, which is equal to 8. Next one, 6p. N is 6, that is principal quantum number is 6 and L value for P is 1, which is equal to 7. Next comes 5p. Dear students, we are following option A. Next is 5p, where N value is 5 plus P is 1, which is equal to 6. Next 4d, where N value is 4 and for D, L is 2, which is equal to 6. So there are 2 orbitals which are having same energy. In such cases, we are going to follow N plus L rule, where higher the N value, higher is the energy. I repeat, higher the N value, higher is the energy. Therefore, 5p will be having higher energy than 4d. 5p is having higher energy than 4d. 5p is having less energy than 6p because the value is less. Next comes 6p and finally we have 5. That is, the given option A is the correct way of representing decreasing order of energies. Question number 1, option A. Moving to the second question. Question number 2. Which of the following pair of d orbitals will have electron density along the axis? So dear students, please remember the d orbitals can be represented as dxy, dyz and dzx, and also dx square minus y square and dz square. These are the 3 orbitals which are having their lobes in between the axis. In between the axis. Whereas these are the 2 orbitals which are having the lobes on the axis. On the axis. That is, we are having x axis and y axis. The lobes are along the axis of x and y. This is called as dx square minus y square. If the lobes are in between the x and y, that is called as dxy. So lobes along the axis indirectly mean that electron density along the axis. So the correct option is option C, dz square dx square minus y square. Question number 2, option C. Moving to the next question. Question number 3. Calculate the energy in joules corresponding to the light of wavelength 45 nanometers. Planck's constant is given. The speed of light is given. There are 4 options. Let us calculate the energy of the light with a wavelength 45 nanometers. So wavelength it is given it as 45 nanometers, which can also be written as 45 into 10 to the power minus 9 meters. We have the formula to calculate energy, E is equal to h nu, which can also be written as hc divided by lambda, where h is Planck's constant and c value is also given. Substitute the values, you will get the answer. So value for h, Planck constant 6.63 into 10 to the power minus 34 joules seconds into c value 3 into 10 to the power 8 meter per second divided by lambda is given, it is 45 into 10 to the power minus 9 meters. Meter get cancelled, per second get cancelled. So answer what we are going to get, it is in terms of joules. Upon simplification, 6.63 into 3, which will get the value around 19.89 into 10 to the power minus 34 plus 8, it is minus 26 joules divided by 45 into 10 to the power minus 9 as it is, which is equal to, upon simplification, so it will take hardly 1 minute to simplify. As I am explaining, it is taking time. So 45 I can write it as 4.5 into 10 to the power minus 8 joules. So 4.5, 19.89, the value what we are going to get is around 4.4 into 10 to the power minus 26 plus 8, which you will get the answer in terms of 10 to the power minus 18 joules. The correct option for question number 3 is D. Going to the next question. Which one is the wrong statement? The uncertainty principle is delta E into delta T is greater than or equal to h by 4 pi. Half-filled and fully filled orbitals have greater stability due to greater exchange energy, greater symmetry, and more balanced arrangement. The energy of 2s orbital is less than the energy of 2p orbitals in case of hydrogen-like atoms. De Broglie's wavelength is given by lambda equal to h by mv, where m is mass of the particle and v is the velocity of the particle. Dear students, it is a theoretical or the knowledge based question. Wrong statement is option C. Because in hydrogen like atoms we will be having only one orbital, and that is 1s orbital. There are no 2s and 2p orbitals. Hence the wrong statement given is option C. Option A, you may confuse with the uncertainty principle. It can be applicable for position and momentum. It can be applicable for energy and time. We cannot predict the exact position and exact momentum in a given time. We cannot predict the exact energy at a given time. If you go for one accurate value, the other will be precise or not accurate. So both can give the equation greater than or equal to h by 4 pi. Second one, half-filled and completely filled orbitals are more stable because of these three reasons. And the last one, de Broglie's equation, it is correct. Lambda is equal to h by p, you can write, or which is equal to h by m into v, that is mass into velocity is momentum. So the wrong statement given is option C. Moving to the next question. Question number 5. If uncertainty in position and momentum are equal, then uncertainty in velocity is. So Heisenberg uncertainty principle we learned delta x into delta p, which is greater than or equal to h divided by 4 pi. If uncertainty in position and momentum both are equal, then what is the uncertainty in velocity? By considering uncertainty in position can also be written as mass into uncertainty in velocity into uncertainty in momentum is mass into delta v, which is equal to h divided by 4 pi, which is equal to m square into delta v square, which is equal to h divided by 4 pi. Therefore, delta v square, which is equal to h divided by 4 pi m square. Therefore, delta v, which is equal to square root of h divided by 4 pi m square. Therefore, uncertainty in velocity we can write it as Root of 4 is 2, that is 1 divided by 2 outside. Root of m square is m, that is 1 divided by m, take it as outside. What is left into the square bracket is h divided by pi. So this is the correct option, 1 divided by 2m square root of h divided by pi is the correct option for question number 5. If uncertainty in position and momentum are equal, then the uncertainty in velocity is 1 divided by 2m square root of h divided by pi. Going to the next question. Question number 6. For a given energy, E is equal to 3.03 into 10 to the power minus 19 joules. Corresponding wavelength is Planck's constant and speed of light is given. There are 4 options given. Let us find out the wavelength. We have the formula E is equal to h nu, which is equal to hc divided by lambda. Therefore, lambda is equal to hc divided by E. Substitute the values, you will get the answer. H is given 6.626 into 10 to the power minus 34 joules seconds into velocity of light 3 into 10 to the power 8 meter per second divided by energy is also given 3.03 into 10 to the power minus 19 joules. Joules get cancelled. Second per second get cancelled. Answer what you are going to get, it is in terms of meter. 6.626 into 3 divided by 3.03. 3.03 and 3 get cancelled. So answer it is in terms of 6.626. As it is 0.03, there is a small decrease in the value, we can consider as 5. 6.5 we can consider into 10 to the power minus 34 as it is, into 10 to the power plus 8 as it is, into 10 to the power minus 19 becomes plus 19 in terms of meter. So which is equal to 6.5 into 10 to the power minus 7 meters. We can take it as 6.50 into 10 to the power minus 7 meters. But with respect to the answers, they are 6.56. So you can take this as 6.56 into 10 to the power minus 7 meters, which can also be written as 656 into 10 to the power minus 9 meters, and which can also be written as lambda is equal to 656 nanometers. So the correct option is option D. Moving to the next question. Question number 7. Which of the following statement do not form a part of Bohr's model of hydrogen atom? 4 options. Energy of the electron in the orbits are quantized. The electron in the orbit nearest to the nucleus has the lowest energy. Electrons revolve in different orbits around the nucleus. The position and velocity of the electrons in the orbit cannot be determined simultaneously. This is the knowledge based question. Energy of the electron is quantized. Quantized means it is fixed for that particular orbit. Energy of first orbit is fixed. Energy of second orbit is fixed. Energy of third orbit is fixed. Similarly, energy of electron in respective orbit, it is quantized. This is correct option, but we need to identify do not form a part of Bohr's atomic model. Electron in the orbit near to the nucleus has the lowest energy. Yes, of course, as we move away from the nucleus, energy of the electron is going to increase. This is one of the postulates of Bohr's atomic model. Electrons revolve in different orbits around the nucleus. Of course, electrons can revolve around the nucleus in a different cells or orbits. Next, the fourth one, the position and the velocity of the electron in the orbit cannot be determined simultaneously. Delta x into delta p, which is greater than or equal to h by 4 pi. The formula it is with respect to uncertainty in position, uncertainty in momentum is given by Heisenberg. So this is not the part of Bohr's atomic model, it is the part of Heisenberg uncertainty principle. Heisenberg uncertainty principle. The correct option for question number 7 is option D. Moving to the next question. Question number 8. Which one of the following set of ions represent the collection of isoelectronic species? There are 4 options given: K plus, Cl minus, Mg2 plus, Sc3 plus. Let us write the atomic number of elements. Potassium is 19, Cl is 17, Mg 12, Sc 21. So this is not the set of isoelectronic species because of Mg. Second, coming to the second one, Na atomic number is 11, calcium it is 20, Sc that is scandium it is 21, and fluorine it is 9. So this is also not the set of isoelectronic species because of fluorine and sodium, or calcium and scandium. Moving to the next one, option 3, potassium it is 19, calcium 20, scandium 21, and chlorine it is 17. So we can consider K plus 19 electrons. Now it becomes 18 electrons because of loss of 1 electron. Calcium it is 2 plus, that is 20 electron minus 2, 18 electrons now. Scandium it is 3 plus, 21 atomic number, minus 3 means 18 electrons. Cl minus 17 electrons, by the addition of 1 electron becomes 18. So all the 4 are having same number of electrons. Hence option C is the correct one for isoelectronic species. A given set K plus, Ca2 plus, Sc3 plus and Cl minus are having same number of electrons. Moving to the next one, question number 9. The correct set of 4 quantum numbers for a valence electron of rubidium, atomic number is 37, is. So rubidium Rb, atomic number Z equal to 37. So in the first period we are having 2 electrons, second period 8 electrons, third period 8 electrons, fourth period 18 electrons, fifth period 18 electrons, like that it goes on. By the addition of electrons, 2 plus 8 is 10, plus 8 18, plus 18 it is 36. It is 36. And now the atom given is having atomic number 37, means n equal to 1, n equal to 2, n equal to 3, n equal to 4. Now this becomes n equal to 5. So the element which is given, that is a rubidium, which is having fifth orbit, n equal to 5. And 36 is a noble gas, and very next member is the 37, which is having n equal to 5, and L is 0 because it belongs to s orbital. It belongs to 5s orbital. So n value we got, it is 5. L value it is belong to s orbital, it is 0. M, if L equal to 0, M is also 0, and S is plus half. So correct set 5, 0, 0 plus half is option A is the correct one. How we calculated? By knowing the elements which are present in different periods. Period number 1, 2, 3, 4, up to 4 it is 36, and next member 37, which belong to first group number 1, that is s orbital first electron. So correct option for question number 9 is option A. Moving to the next one, question number 10. Which of the following set of energy of possible excited states of hydrogen is? So here hydrogen atom is given, which is having an electron n equal to 1. So which is having electron in the first cell. There is a nucleus at the center. This is the first orbit and this is the second orbit. In the first orbit there is electron and it has to jump to its possible excited state, that is n equal to 2. So the electron is excited to its higher n equal to 2 orbit. Therefore energy with respect to nth orbit is minus RH z square divided by n square. For hydrogen z equal to 1, and for second orbit n equal to 2. Therefore E2, which is equal to minus RH 1 divided by 4. So RH value with respect to electron volt we have is 13.6 divided by 4, which gives the answer 3.4 electron volt, that is minus 3.4 electron volt. The correct option is option C for question number 10. Which of the following energy or possible excited state of hydrogen is C 3.4 electron volt by considering n equal to 2, where it is an excited state for hydrogen atom with 1 electron. Moving to the next question. Question number 11. The radius of second Bohr orbit of hydrogen atom is Planck's constant is given, mass of electron is given, charge of electron is given, permittivity of vacuum is also given. So to identify the radius of second Bohr orbit, we have the formula Rn is equal to, in terms of Armstrong unit, 0.529 n square divided by z Armstrong unit. What we need is Bohr's orbit and atomic number of given atom. So here the hydrogen atom is given, atomic number is 1, and we need the radius of second Bohr orbit n equal to 2. The other things which are given, it is not necessary. So then why these all quantities are given? Just to confuse you people. So what is to be substituted? 0.529 as it is into n square, it is 2 square, which is equal to 4, divided by 1 in terms of Armstrong unit, which is equal to, the answer what we are going to get is 0.529 into 4 times is 0.5 into 4 times means it is 2 point. So it is 2.116 Armstrong unit. So the correct option is option C. The radius of Bohr second orbit of hydrogen atom is, that is R2, which is equal to 2.116 Armstrong unit, which is also equal to 2.12 Armstrong unit. Moving to the next question. Question number 12. The spectrum of helium is expected to be similar to which of the following? Hydrogen, lithium ion, sodium, helium ion. Which is the correct option? It is the spectrum of helium means the spectrum whatever you are going to get, it is because of number of electrons. So helium atom is given, helium atom which is having atomic number 2, that is Z equal to 2, which is also equal to number of electron if it is neutral. As helium atom is given, it is neutral, that means number of electrons in helium atom which is equal to 2. So which of the following option is having 2 electrons? Hydrogen is having only 1 electron. Lithium plus, lithium if it is neutral, it is 3 electrons. If you remove 1 electron, it becomes Li plus, and the number of electrons are 2 and the atomic number 3 remains as it is. So number of electrons 2 in case of Li plus, and which is the correct option, which gives the similar type of spectrum as expected for helium. Whereas in case of sodium, atomic number is 11, means there are 11 electron and it is neutral. Helium plus, which has lost 1 electron, there is 1 electron left now. So the correct option for question number 12 is option B, lithium plus ion. Going to the next question. Question number 13. If electron falls from n equal to 3 to n equal to 2, then emitted energy is, electron fall from n equal to 3 to n equal to 2. That is, excited state is 3 and initial state is 2. Initial state was 2 and final state was 3. So it means the electron is coming from third cell to second cell. This is the amount of energy emitted, and emitted energy is always positive because it is liberated energy. Therefore, total energy which is equal to energy of final cell minus energy of initial cell, whatever the amount of energy is released, that is emitted energy, which is also equal to RH into the bracket 1 divided by Ni square minus 1 divided by nf square. By substituting the value with respect to electron volt, RH value for electron volt is 13.6 into bracket 1 divided by initial is 2, 2 square is 4 minus 1 divided by final is 3, 3 square is 9, which is equal to 13.6 into 5 divided by 36, which is equal to 68 divided by 36, which is also equal to 1.88 electron volt, which can also be written as 1.9 electron volt. So the correct option for electron fall from n equal to 3 to n equal to 2, then the emitted energy is 1.9 electron volt, that is option C. Moving to the next question, question number 14. Principal, azimuthal and magnetic quantum numbers are respectively related to size, shape, orientation, shape, size, orientation, size, orientation, shape, none of the above. Principal quantum number n, which is going to represent size of atom or size of orbit, you can consider. Here we have the nucleus. This is first orbit, this is second orbit, this is third orbit, where n values are going to increase. Hence, size of orbit is going to increase. Next, coming to azimuthal quantum number, it is going to represent the shape of atomic orbital, shape of orbital. Shape of orbital it is going to represent, where s orbital is spherical, p orbital is dumbbell, d orbital is double dumbbell, and f orbital is triple dumbbell. Like that, the shape is decided by L, that is azimuthal quantum number. Coming to magnetic quantum number, it is going to represent the orientation of atomic orbital. Orientation of atomic orbital. That is, considering p orbital, there are px orbitals, py orbital and pz orbital. There the lobes of p are along the x-axis, along the y-axis and along the z-axis. It is represented by magnetic quantum number. That is orientation of atomic orbital for magnetic quantum number, shape of atomic orbital for azimuthal quantum number, size of orbit for principal quantum number, size, shape and orientation. That is option A. The principal, azimuthal and magnetic quantum numbers are respectively related to size, shape and orientation of atomic orbitals. Moving to the next question, question number 15. The orbital angular momentum of 4p electron will be. So for orbital angular momentum, we have the formula L is equal to square root of L into bracket L plus 1 H divided by 2 pi. Here we have 4p, where n, that is principal quantum number, is 4 and L, azimuthal quantum number for p is 1. Remember, L value for s is 0, for p is 1, for d is 2 and for f is 3. So by substituting L value, we are going to get the answer L into bracket L plus 1, that is 1 into bracket 1 plus 1 H divided by 2 pi, which is equal to root 2 H divided by 2 pi is the answer. So orbital angular momentum of 4p electron will be root 2 H divided by 2 pi, that is option B. Moving to the next one, question number 16. If charge of electron is 1.60206 into 10 to the power minus 19 coulomb, charge to mass ratio is 1.75875 into 10 to the power 11 coulombs per kg, then the mass of electron is, there are 4 options given. Dear students, there is a simple way to calculate mass of electron. So what is given? Charge of electron is given. It is 1.602, we can consider, into 10 to the power minus 19 coulomb. And charge to mass of electron is given 1.758 into 10 to the power plus 11 coulomb per kg. Okay. What we need to get is mass of electron. Therefore, E by me, which is equal to 1.758 into 10 to the power plus 11 coulomb per kg. Therefore, mass of electron, which is equal to E divided by 1.758 into 10 to the power 11 coulomb per kg. Therefore, mass of electron, which is equal to charge of electron, is 1.602 into 10 to the power minus 19 coulomb divided by 1.758 into 10 to the power plus 11 coulomb per kg. Coulomb get cancelled, which is equal to 1.6 divided by 1.7 means it is 0.91 into 10 to the power minus 19 into 10 to the power minus 11 kg, which is equal to 9.1 into 10 to the power minus 19 minus 11, it is minus 30. Here we shifted one decimal, hence it is minus 31 kg. So the correct answer is option B, 9.1091 into 10 to the power minus 31 kg. Next question, question number 17. Which of the following series of transition in a spectrum of hydrogen atom falls in visible region? Dear students, it is knowledge based question. It is the correct answer is Balmer series. Lyman series fall under UV radiation. The first series of spectral lines of hydrogen is identified in Balmer series. It is visible region. Next, Passion series, infrared region, Bracket series, infrared region, and P-Fund series also in infrared region. Hampre series, a new series of spectral lines, Hampre series, which is identified in far infrared region. This is the new spectral lines which are obtained Hampre series, far infrared region. So question number 17, the series of transition of spectrum of hydrogen fall under visible region is Balmer series. Visible region, Balmer series, option B. To the next question, question number 18. The energy of second Bohr orbit of hydrogen atom is minus 328 kilojoule per mole. Hence, the energy of fourth Bohr orbit would be. There are four options given. So, there is a relation between energy of second orbit and energy of fourth orbit. So, we have the formula minus RH Z square divided by N square. N equal to 2, we can consider it as N2 square. For E4 minus RH as it is, Z square divided by N4 square. So here what we are going to get is E2 divided by E4, which is equal to minus RH get cancelled. Both belong to hydrogen atom, so we can consider 1 square 1 as it is. 1 square is 1 divided by second orbit, 2 square is 4 divided by 1 square in 1 divided by fourth orbit, 4 square is 16. So energy of second orbit is given as minus 328 kilojoule per mole divided by E4, keep it as it is, which is equal to 1 divided by 4 into 16 divided by 1. So here we are going to get a simplified equation E4, which is equal to minus 328 divided by 4 kilojoule per mole, which is equal to the answer what we are going to get is 82. 4 1s are 4, 4 8s are 32, 4 2s are 8. So therefore minus 82 kilojoule per mole is the energy of fourth Bohr orbit. Option D is the correct one, minus 82 kilojoule per mole. Moving to the next question. Question number 19. The statement that is not correct is energy of stationary state in hydrogen like atom is inversely proportional to the square of principal quantum number. So energy of nth orbit, which is equal to minus RH Z square divided by N square, where RH and Z are constant. Therefore, energy of nth orbit is inversely proportional to square of principal quantum number. The first option given it is correct, but we need to identify which is not correct. The radius of first orbit of helium plus is half of the first orbit of hydrogen atom. So we have a formula Rn is equal to will go with respect to 52.9 n square divided by Z, where n for helium is 1, for hydrogen is also it is 1, so therefore which is equal to 52.9, keep it as it is, divided by Z. For helium it is 2, that is Z equal to 2 for helium. So for helium 52.9 divided by 2, which gives half of the radius of hydrogen atom, because for hydrogen atom Z equal to 1. So the second option given is also correct. Moving to the third one, the angular quantum number signifies the shape of orbital. Angular quantum number or azimuthal quantum number both are same. So angular quantum number L, which is going to represent the shape of orbital. That is, for S it is spherical, for P it is dumbbell, for D it is double dumbbell, and for F it is triple dumbbell. These shapes are identified by azimuthal quantum number, also known as angular quantum number. Hence option C is also correct. Coming to the fourth one, the total number of nodes for 3s orbital. So we have a formula to calculate nodes. In case of 3s orbital, that is s orbital always gives spherical nodes or radial node. We have the formula n minus L minus 1. Therefore, for 3s orbital n equal to 3 minus L value for s orbital is 0 minus 1 as it is, which is equal to 2. But here option it is given as 3. Hence, the statement which is not correct is option D. The number of nodes for 3s orbital is 2. Moving to the next question. Question number 20. The radius of the first Bohr orbit of hydrogen atom is R. Then the radius of first Bohr orbit of lithium plus 2 will be. Four options are given. We have the formula for radius of Bohr's nth orbit is Rn is equal to 52.9 n square divided by Z picometers. Considering hydrogen atom where Z equal to 1 and hydrogen atom first Bohr orbit where n equal to 1, therefore R1 of hydrogen atom which is equal to 52.9 only, but it is given as R. Therefore radius of first Bohr orbit of hydrogen atom which is equal to R. Considering lithium plus 2, Li2 plus, radius of Bohr first orbit of lithium plus 2 which is equal to 52.9 n square divided by Z picometers is the formula, which is equal to 52.9 n square by Z for hydrogen atom is R. Therefore, by considering 52.9 n square as R and for lithium Z equal to 3. For lithium Z equal to 3. Therefore, the answer for lithium first orbit radius will be R by 3 if radius of hydrogen atom is R. So the correct option is option B, R divided by 3. Here it ends the session. Hope you enjoy the session. Thank you all.